Hello everyone. So we are going to start the last part, that is the part 7 from the topic Rheology. So in this topic we are going to learn about the remaining type of viscometer. Moreover, the actual application of the Rheology in the manufacturing of pharmaceutical dosage form. So without wasting any time, let's start our presentation. So the next type of viscometer, it is your cone and plate type of viscometers. So as the name reveals, so it is generally considered under a rotational viscometer, and as the name reveal, it have a cone and a plate. So this is their structure, you see. So here we'll have one cone and one plate. The substance of which we want to determine the viscosity will be placed in between this cone and plate. So here we have shown a paste, it is placed between the plate, right? So here a motor will be fitted. The motor will produce a angular velocity, by virtue of which this cone will be revolving over this plate. This is the radian, and this is the radius of the cone, and this is the distance. So what actually happens and what is the principle? So principle is simple, that the sample will be placed on at the top center of the plate, right? Here the sample will be placed and which is raised into the position under the cone. So now the cone, it is driven by a variable speed motor. A speed motor will be connected here, right, which have a variable speed, means it can be, the speed can be increased or it can be decreased based on our wish. So the cone will be driven by a motor, and the sample, it will be sheared. The sample will be sheared in the narrow gap between the stationary plate and the rotating cone, as because the cone will be rotated due to its attachment to the motor. The plate will remain in a stationary position. So this cone will be rotating, and by virtue of this rotating force, the cone will be applying the shear stress over the sample, right? Now the rate of shear in RPM, actually it is increased and decreased by a selector dial. Here will be a dial, by just like your fan which we use in our home, right? We can, by using the regulator, we can increase the speed of the fan as well as we can decrease the speed of the fan. Similarly, here there will be one dial. This dial will help to increase or decrease the speed of the cone, right? And the viscous traction or torque will be produced on the cone. As this cone will be revolving, viscous traction or torque will be produced on this cone, right? So viscosity for Newtonian system can be estimated by simple reaction or simple equation here, that is eta is equal to Ct divided by V. So where C, it is the instrument constant, this T, it is the torque reading, and this V, it is the speed of the cone, that is angular velocity, and plastic viscosity determined by a different equation here. U is equal to CF Tf by V. So what is that? Number one, yield value F. Yield value F, it is equal to CF into Tf, right? This is the yield value, CF into Tf. And Tf is what? It is the torque at shearing stress axis. I repeat, Tf, it is the torque at the shearing stress axis. It can, how we are going to get this torque? Just simply we have to extrapolate it from the linear portion of the curve. So Tf, it is the torque at the shearing stress axis, means the line which is drawn from the top to the bottom crossing via the cone, right? And the Cf, it is the instrument constant. Tf, it is the torque at the shearing axis. Now the rheology of pharmaceutical system. So you see basically suspension and emulsion. Non-Newtonian rheological profile. This suspension and emulsion, they show non-Newtonian rheological profile. Mixing process, generally it affects the viscosity of the formulation, right? This formulation may have shear thickening system. Now we all know that what is shear thickening. Upon application of the shear stress, the system may get viscous or it may get thick, right? So for shear thickening system, high viscosity can have a significant effect on the content uniformity of the drug. Now what is that? This is a big issue. See, for shear thickening system, if the system is a shear thickening system, and if we have added some constituent which is having a high viscosity, then this can lead to non-uniformity of the drug. Means every time you are taking out the drug from the container, you might not get the equal amount of the drug. The drug content will be different, as because the drug may agglomerate, the drug may settle down, something like that, right? So the settling and aggregation of the solid particles in the suspension are viscosity dependent. We know that the settling and the aggregation of solid particles which are present in a suspension, these are viscosity dependent. If the viscosity is too high, then they will remain suspended, and if the viscosity is less, then they will definitely come to the bottom, right? So the emulsion stability is viscosity dependent. We know that. So use polymeric emulsifier. So what polymeric emulsifier we can use? We can use like polyacrylic copolymer. Actually, these increase the emulsification as well as they increase the viscosity. Clear? The next one, it is your ointment and ophthalmic drops. So you see, the viscosity of ointment, it increases upon addition of drug and excipient. We know that, right? Now it is, once the viscosity increases, it becomes very difficult to remove the product from the container, right? Whenever you have some product in the tube, suppose if the product is very viscous, it is very hard to take out the content from the tube, right? So it is generally a problem to the elderly patient, right? And moreover, as the product is very viscous, upon application of this product to the affected area, they don't get easily spreaded. They don't get easily spread over the skin surface, and thus it becomes less efficacious, right? So to troubleshoot such problem, what we can do? You see, very small volume, approximately 10 microliter of ophthalmic drop, which remains after blinking. Suppose we have put some ophthalmic drop in our eyes. So after blinking of the eyes, most of the ophthalmic drop, it comes out from the eyes, right? From the, suppose we have, in simple language, we have put some eye drop in our eyes. After blinking of our eyes, most of the drug, it comes out, or the formulation, it comes out. Approximately almost 10 microliter of the drop, it remains over the surface of the eye, right? So increase the viscosity. If we increase the viscosity in such cases, it will retard the drainage. Retard the drainage means what? The ointment, or the means eye ointment, or eye, sorry, not the ointment, the eye drop, it will not come out, right? Which will retard the drainage and increase, definitely it will increase the contact time. More time, the drug or the ointment or the your ophthalmic drop, it will remain in contact with your eyes, and it is thus increase the bioavailability, right? So in such cases, what we can do? Use hydrophilic polymer. Example of hydrophilic polymer are polyvinyl alcohol, PVA, and HPMC, that is your hydroxypropyl methyl cellulose. So in ophthalmic solution, we can use some polymer which can increase the viscosity. This polymer also can retard the drainage of the product from the eyes, and thus it will increase the contact time and increase the bioavailability. Thus it makes the drug much more efficacious for the treatment of any sort of disease of the eyes. Clear? The next concept is your polymeric gel or polymer gel. So we know that what is a polymer gel. So polymer gel, actually these are the solid, semi-solid system, and this polymer gel, they are made of the polymer, but they are interpenetrated, means this polymer chain will be penetrated. These are the polymeric chain. These will be penetrated with, interpenetrated with what? With the solvent, that is generally the water. So gel is formed by physical cross-linking. This polymer, they will cross-link with one another. This polymeric chain, they will cross-link with one another. They will form a 3D structure, three-dimensional structure, that is the gel, right? They will form by cross-linking and non-covalent forces, just like your hydrogen bonding and hydrophobic interaction. So gel generally exhibit viscoelastic property, and these material are there. These are generally the rigid material at the rest, and this gel, you can see whenever you apply the gel over your hair also, they flow when the shear stress is induced. Generally what we used to do, we used to take out the gel and we used to put it in our palm. We just rub the two palm of the hand, right? This gel, it immediately get converted into sol, that is your solution. Clear? Now the next concept, it is in situ gelling. What do you mean by in situ gelling? Simple. These are those substances which initially remains in the liquid form or solution form, but upon change in the physical parameter, they get converted into the gel. They might be getting converted over the surface of your body. Let's have some example. Right, so you see a process of gel formation, actually in situ gelling, at the site of application after the composition or formulation has been applied to the site. The formulation has been applied to the site. After the application of the formulation, the gel will be formed. So what you can use in such cases, for in situ gelling process, we can use gel and gum, alginic acid, we can use xyloglucan, pectin, chitosan. This is the poly-D-L-lactic acid or poly-D-lactotide and co-glycolide. This is the PLGA, and polycaprolactone. These are different polymers which can be used for in situ gelling. Let's have some example. You see, these are example of some drug. Theophylline. This theophylline drug, it is generally used as a bronchodilator in case of asthma, right? So in the formulation of the theophylline, if we use the gel and gum, but why it is used? It is a in situ gelling agent. It is generally given by oral administration. If we use the gel and gum, you see 4 to 5 fold increase in the bioavailability in rats have been reported. Means if we use some in situ gelling agent, the bioavailability means what? The rate and extent of the drug available in the body, which can be used for therapeutic utility. I repeat, bioavailability means the rate and the extent, means the rate and concentration of the drug. That is your unchanged drug, which can be used for therapeutic action. So the rate and extent of the drug available in the body. So if we use the gel and gum, we can increase the bioavailability of the theophylline up to 4 to 5 level. The next one, it is the doxorubicin. In the case of the doxorubicin formulation, you can use HSA, that is your human serum albumin along with tartaric acid derivative. It is generally formed in the injectable form. If we use this human serum albumin, then it can deliver the drug for a long while. You can achieve the sustained delivery of the drug. Similarly, for testosterone, we can use the polylactic acid and PLGA, which will actually slowly it will release the drug. So these are different examples actually. Even you can find it for paracetamol and ambroxol. Right, in the formulation, if we use the pectin, it's generally given by oral oral route of administration, and if we use the pectin, we can achieve sustained oral delivery. Clear? So in the in situ gelling, actually you see there are types of gelling process. Number one, it is your temperature sensitive polymeric formulation. So you see it in a temperature sensitive polymeric formulation, it's changed from a liquid to gel consistency at a critical transition temperature. Means the polymer need to achieve a temperature at which this polymer will get converted from the solution or from the liquid form to the solid, that is the gel form. Means it need to achieve that particular temperature. So generally there are some polymers which are temperature sensitive, means after reaching the temperature they are going to get converted from the liquid to the solid. For example, your pruronic F127, it is also known as Poloxamar 407. It generally need 21 degrees centigrade or 69.8 Fahrenheit to get converted from the solution to gel. This temperature, it is expressed as T sol to gel is equal to 21 degree centigrade. So this is one type of parameter or attributes, you can say. This is known as the temperature sensitive conversion. Temperature sensitive conversion means upon reaching the temperature, the liquid will get converted into the gel. Clear? Apart from that, you see this polymeric system, they can also get converted from the liquid to gel consistency as a result of ionic interaction. This is the different type of mechanism. Earlier one, that was they are generally temperature sensitive. Now due to the ionic interaction, for example the Gelling gum, they change from liquid to gel in the presence of monovalent cation. Example of monovalent cation, sodium and potassium. If we are using the Gelling gum and if we are using sodium or potassium, then immediately the sodium and potassium can be converted, immediately the Gelling gum can be converted into gel. Earlier the Gelling gum will be in the liquid form, but if we add sodium or if we add potassium, due to ionic interaction, they are going to get converted into gel form. So this is a compound, you see, timolol maleate. So actually in this timolol maleate, you see ingredients, Gelling gum is there, right, mannitol is there, and along with that we are going to have either your sodium or you are going to have your potassium, and this is used to convert the solution into the gel form. Clear? Now viscosity modifier. So we have a list of viscosity modifier. There are different types of viscosity modifier which are used in the pharmaceutical dosage form just to increase the viscosity or to decrease the viscosity based on the requirement. We have this chart. See, cellulose derivatives. These all are cellulose derivative, means they are derived from the cellulose. They can be used as a viscosity modifier. Example, methyl cellulose, sodium carboxy methyl cellulose, hydroxy ethyl cellulose, hydroxypropyl cellulose, hydroxypropyl methyl cellulose. This is the HPMC. Natural gums. These are the natural gums which can be used as a viscosity modifier. Example here, acacia, tragacanth, xanthan gum, carrageenan. Moreover, we have sodium alginate. Directly sodium alginate can be used, right? Then we have polyacrylic resin like your homopolymer resin, copolymer resin, sodium salt resin, and even we have the poly and vinyl pyrrolidone resin. We can use pluronic copolymer, as we have already discussed regarding the pluronic, right? It is the poloxamer. We can use even the clay. Example is your bentonite. Bentonite can be used to modify the viscosity. Clear? Let us take the example of HPMC. Oh, what is a HPMC? So this is the chemical structure of HPMC. You see, HPMC actually it is a typical substitution of the cellulose. HPMC consists actually 15 to 30% of the methoxy group. Moreover, it have 4 to 30% of the hydroxypropyl group. I repeat, in the HPMC we have 15 to 30% of the methoxy group and 4 to 30% of the hydroxypropyl group. A factor which influence the organic solubility, thermal gelation, temperature of the aqueous solution. So these are the factors. Actually the methoxy group as well as the hydroxypropyl group, they generally, their concentration generally influences the organic stability of this polymer HPMC, their thermal gelation, temperature of the aqueous solution, right? So non-ionic polymer, they does not have incompatibility issue with cationic compound. I repeat, non-ionic polymer. Non-ionic polymer means they are neutral polymer. They don't have incompatibility issue with the cationic compound. Clear? Next step of your cellulose derivative viscosity modifier, it is your methocell. So methocell, it is also known as generally methocell cellulose, and it is the cellulose ether. Actually these are cellulose ether. They are water soluble methyl cellulose. Methocell, this is a water soluble methyl cellulose, and hydroxypropyl methyl cellulose polymer, it is also known as dough chemical, right? So this is the molecular weight. You see molecular weight of the methyl cellulose as well as the hydroxypropyl methyl cellulose. This is their concentration. It is used in the different concentration to be used as a viscosity modifier, and it is the shear rate, the how they means they respond to the shear rate, right? So I hope you have enjoyed the video. If you like the video, just press the like icon. You can share this video and you can subscribe to my channel. Thank you once again.